Hello guys, welcome to today's Yebo Physics session. So for today we'll start with FVV 101 questions from section 8 of the workbook. And we'll look at these questions through to section 8.3, then I'll switch over to the PHYV practice quiz questions from the module side. So I hope you guys have been doing well so far, and you are finding this channel helpful. So as usual, we do encourage you guys to participate, to chat with us. You have to use the chat box on YouTube or the one on Teams if you want to call in or to speak with us. You can use Teams to be able to get through. You'll be able to get through to us, and I will be able to hear you and address your questions or hear your contributions. So please feel free to participate and benefit much. Participation is very important. It will help you and even your colleagues with questions that each of us may have. So without wasting much time, we'll just go over the sections 8.1 to 8.3 of the workbook. And I think I've already set the recording on Teams and the platform is up and running. So if you want to join us via Teams, please feel free to do so. The link is the same always, so you can just use click that link and connect to the Teams platform. So the section 8 of the workbook is a section on Newton's laws. And we need to have a detailed understanding of these laws and how they apply and what their consequences are. So they are very significant when it comes to dealing with motion and dealing with forces and how the different objects would behave under different conditions. So we can have cases whereby the friction can be included in the setup. We can have cases where friction is neglected. So those cases will apply differently because there is a tendency of an effect of that frictional force on the motion of the object, which is basically an extra force that tells you that your net force will be kind of different from what you'd have if you had neglected friction. So the first part of the workbook, let me just try and scroll through it. We see there's a part which says distinguish between mass and weight, which is a very important distinction that we need to make there. And basically from definitions, mass being the amount of matter an object can have, and weight is the force of gravity that acts on mass. So the two are carelessly used at times whereby someone says we're measuring mass and they give that mass in newtons. That is typical of people, I think, from chemistry, and people in medicine, they just say we're measuring the weight when they are actually measuring also mass. So anyway, in this course, mass and weight are strictly different. So when we look at mass, we are measuring the amount of matter an object can have, and we measure that in kgs. When we look at weight, we are looking at the force of gravity that acts on the mass, and that is given in newtons. So it's a force, it's given in newtons. Mass is a scalar, weight is a vector. So those two quantities are completely different. Though they are related, as force is that force which acts upon mass to give us the weight. So inertia is the measure of or mass is given as the measure of a body's inertia. So inertia being the reluctance of a body to start moving if at rest or to stop moving if in motion. So it is the tendency of a body to want to remain in its state of uniform motion, which is what is explained by Newton's first law. So it is a consequence of inertia, and stated that law would simply say that a body would remain in its state of rest or uniform motion, or that's in a straight line, which is uniform velocity, unless it is acted upon by a net external force. So in some texts you'll find it just says external force, but net external force would simply mean that external forces can act at times on a body, and if those external forces balance up, the body will still obey Newton's law. Right, we'll talk more about this when we look at some questions which are following. But if there is no net force, meaning if the external forces are such that they are balanced, there's no net force, then the body should remain in its state of motion, which is, it can be rest or it can be uniform motion or state of constant velocity. So that's a consequence of inertia, meaning if a body is initially at rest, it would want to remain at rest unless, or it would remain at rest and want to remain at rest. When you move it, it will, usually you feel this when a car moves suddenly or a plane takes off, you'll tend to lean forward towards your seat because you want to maintain, or you have a reluctance to moving when you are compelled to move while you are at rest. And if it comes to a sudden stop or sudden brakes, if you don't have your seatbelt, which is a very dangerous thing to do, is during application of emergency brakes, you would jerk forward or otherwise be thrown off your seat. So that's inertia, which compels you to want to continue in a state of motion, and that's what Newton's first law is about. So yeah, all the other concepts and the other laws, we'll talk about them as we go. And define all these objectives that are described here. So the concept of a force, the force basically is described as a push or a pull exerted upon an object. So it has a tendency of shifting the state of motion of a body or shifting position of a body, but it can be in the form of a push or a pull. Right? So one other important thing is forces are vectors. When we fully describe a force, we give it in terms of magnitude and direction. So there we have the law of motion stated. The first one, a body remains at rest, or if in motion, remains in motion at a constant velocity unless acted on by a net external force. There we are, net external force. So if it is not a net external force, if there is no net external force, meaning if there is an external force and there is no net force for them, or for the forces acting on that, external forces acting on that body, then it will still remain in its state of rest. So this unless part will not apply. It can, meaning if we have a 50 Newton force, a body moving, constant velocity v, being pushed this direction by a 150 Newton force, and there is friction on this body due to the surface. It's a force that opposes motion, so it's in the opposite direction, and it's 150 Newton. So these two are external forces acting in opposite directions, and the net external force there is equal to 0 newtons. This body remains in its state of uniform motion. It remains moving at a velocity v. That's basically one of the consequences of this law. Other than considering a body that is just at rest and it gets a net force which takes it in motion, or a body that's in motion and there's a net force which stops it. Those are like other cases in which Newton's first law simply applies. But the significance there is when we deal with forces, and forces, external forces are there, and these external forces are such as to balance, then still the law should apply. So it's not an ideal law where we say in a real life situation, this law would apply if we neglect friction. It applies even if there is friction. But once we overcome that friction, then the body would want to remain in that state of motion. Okay, so let's see, define inertia. We have defined these true or false questions. We'll answer these ones. This should be quite simple. A stationary object must have no forces acting on it. Okay, right. These are interesting questions, though. So if a body is stationary, does it mean no forces are acting on it? No, it doesn't mean that. It just means there's no net force, but the forces could be there and balanced. So stationary also in the same sense, if V here is equal to 0 and we still have the same forces balanced like that, then this body will not move. it will remain stationary. So a stationary object is not necessarily one that has no forces acting on it, but it's one where all the forces are balanced and it's not moving, right? There can be balanced and it can be moving at constant velocity. So take note of that concept. The idea of balancing forces is just saying there is no net force, meaning there is no acceleration, which is a result of the second law now, right? So if no net force, no acceleration. So the body can continue constant velocity or can continue with the same velocity, which can be zero, meaning it continues at rest. So this part one is a true-false question. True or false question, which says a stationary object must have no forces acting on it, and our answer here is that one. Our answer is false. A stationary object it does not only have no forces acting on it, it can have the forces acting on it but balanced. Then the next part, for an object to move at constant velocity, it must have a net force acting on it. If no net force was applied to the object, it would come to rest because of its inertia. There we are. So from what we've said, how would you answer this one? What's your answer to this one? What's your answer to this one? If you heard what we said when we started the description of the first law and inertia, for an object to move at constant velocity, it must have a net force acting on it. Is that true? No, it's not. So already, even before we go further, we say false there. Because a body can move at constant velocity only when the forces present on that object are balanced, meaning when the net force is zero. So it must not have a net force acting on it. So if no net force was applied to the object, it would come to rest. No. The net force might bring it to rest, yes, if it is opposing motion, or it might accelerate it. But if no net force is applied and the forces present are just balanced, then the body should remain in its state of constant velocity. Okay, so that's number 3. Number 4, a spaceship floating passively through space has no forces acting on it. A spaceship floating passively through space has no forces acting on it. So if it has no forces, is it moving at a constant velocity? And we said constant velocity doesn't mean there is no force there, right? Doesn't mean there is no force. It's probably forces are balanced. But now this is through space, and if it's floating passively, that should mean it has no acceleration. So what can we say? Space usually is considered close to a vacuum, right? So which means there is no friction there. There is no air friction, or you call it air resistance. Then if it's not accelerating also, then there's no net force. So ultimately, that spaceship should just continue at whatever velocity it has without any net force, or without any force opposing its motion. So that is very possible. That is very possible. So if it's through space, space is considered vacuum, right? So if it floats passively through space, it would move or float through space with its constant velocity, whatever velocity it would have attained as it gets into space, and it continues at that velocity without any external force. But if it accelerates, then that would mean that the acceleration is a consequence of net force. So for this one, I would say this is true. There are no forces acting on this spaceship if it's floating passively through space. And Okay, there's an issue of gravity, by the way. Remember, there's gravity. What do we say about gravity in this case? Maybe the idea of weightlessness there, at a point where maybe gravitational fields tends to cancel out. That can be a case whereby this is, but still they're there. So it means we can't have a case whereby we say no forces, right? Still, it means they're still there, but there's no net force. There's actually no net force. The forces are there. So this question, you have to be careful. No forces is different from no net force. So the forces are still there because it's still in a gravitational field. So yes, I think that is the correct answer to take. The forces, there's gravity still acting on this spaceship. So yeah, you should look at the picture broadly. It's still in a gravitational field, and we said forces can be a push or a pull. It can be acting like they can be physical forces, or they can be non-contact forces like gravity. So still there is force acting on it. It can only be counterbalanced by another reaction force to allow it to float passively through space. All right, so the best choice there would be false. And number 5, a car riding at constant velocity has no forces acting on it. Another one, which is false. So I think it's almost the same case. We have forces being balanced, the driving force and the frictional force, or the resistive forces balancing out. Doesn't mean there are no forces. Remember, no net force doesn't mean no force, right? It means the forces are there, but in equilibrium. Okay. Then the second law, the law that relates the net force to the state of motion of an object in terms of acceleration, right, of an object of mass m. So the acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system. So acceleration directly proportional to and in the same direction as that next external force that acts on the system. And it is inversely proportional to its mass. So the acceleration there is a result of a net external force that acts on the system, and it is proportional to that force, and it is in the same direction as that force, but inversely proportional to the mass. So this is Newton's second law, which is a consequence of the net force. So the relationship there is given. Let's see if we can have some questions. The SI unit for force is the Newton, yes, and express 1 Newton in terms of fundamental SI units. Okay, so we measure force. The unit there is the Newton, where the formula given from the formula force equals to mass times acceleration. Then it means with the units of force should be equivalent to the units of mass multiplied by the units of acceleration. And the units of force we say is the Newton, and the units of mass is the kg, and acceleration is meter per second squared. Okay. So that means 1 Newton is equivalent to 1 kg meter per second squared, and this is the equivalence of the Newton in fundamental SI units. 1 Newton equals to 1 kg meter per second squared. So this is a negative sign per second squared. Okay, which has more inertia, a kilogram of cotton balls or a kilogram of gold? So a kg is a kg. We said mass is a measure of a body's inertia. And in this case, if it's a kg of cotton, it's the same kg with what we get from gold. So the inertia is the same. There is no more none of the two has more inertia if they are all in kgs. Then the third law, whenever one body exerts, is there anything else to say there? Okay, when we said force and acceleration are in the same direction, they are also proportional. So we increase the force, we should increase the acceleration for a constant mass. At constant mass, increase force, you proportionately increase the acceleration. So that's the relationship, and the force and that net force. So the idea of net force now is not just force that we're dealing with here. This is a net force. So the forces can act on a body, but the force or the quantity that is responsible for the acceleration is the net force, which is the interaction between the two objects. So now, if I go back to my diagram, and we have friction 150 and a forward force of 450 newtons, then this body will not move at a constant velocity. This body will now accelerate. This body now accelerates. So initially this was velocity, but this time we have acceleration, so which is change in velocity over time. All right. So the acceleration is proportional to 450 minus 450 is in the positive direction and 150 is in the negative direction. So we add the forces F1, 450, F2, 150, negative. So F net equals to F1 plus F2 is the total force, net force. F1 is 450, is positive. F2 is negative. So this is where we get minus 150 newtons. And 300 newtons becomes the net force. The net force is 300 newtons. And this is the force that gives acceleration. So if we have a block there, and the block is 50 kgs, right? So if we have a block and a block is 50 kgs, then we have 300 newtons equals to 50 kgs times A. Then we get the value of acceleration by dividing by 50 kgs both sides. So it means acceleration can also be given in terms of newtons per kg. So this is that 6 newtons per kg, which is equivalent to 6 meters per second squared. That's our acceleration. So because if we are giving it as a vector, this is just magnitude. If we are giving it as a vector, it's in the positive x direction. Plus, so we can put a plus there to show that this is a vector. Or you can use the axis. This is I, so unit vector I, in the direction of the unit vector I in the x direction. So that's how we present vectors, and if the question requires you to give magnitude, then you can just deal with the magnitude as is. Okay, so let's look at Newton's third law. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. So whenever a body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. So when body A exerts a force on body B exerts an equal but opposite force on body A. That's basically what this statement means. So simply put, action and reaction are equal but opposite. So this is an action-reaction law. And forces will always occur in pairs, and one body cannot exert a force on another without experiencing a force itself. So this is how the bodies interact. So we are referring to this concept when we talk about action-reaction pairs of forces. 3 examples of these pairs of forces are: when you sit on your chair, the action is from your weight, the reaction is from your seat, right? Ultimately, that's between the chair and the ground. Then the action is the weight of your body plus the weight of the chair, and the reaction is the reaction from the ground to the chair, right? So it's to the chair, then to you. So that's action and reaction forces at the point of interaction. The other one can be for a flying plane, it's the weight and the air, right? The weight of the aeroplane, of the aircraft, and the reaction force from the air giving the upthrust. So that's basically an action reaction similar to a floating body or a boat on water. The mass of the boat is the action. The reaction will be the upthrust from the fluid. So you can think of a number of them. If something collides or hits a wall, like when you hit a billiard ball, that's when playing maybe snooker or playing pool, you strike that ball with your stick. The ball will move, of course, but at that point of interaction, the force that you apply on the ball is the same force by which the ball reacts onto the stick, right? So because your force tends to be an unbalanced force, then the ball will simply move to the other side. But at the point of interaction, the action and reaction will be equal but opposite. So during a collision, that's example number 9. During a collision between a truck and a pedestrian. I see someone just joined us. Can you hear anything from your side? I hope the audio is okay. Usually when people don't confirm, we would not be, everything will be okay here in the studio, but maybe at times there tend to be some technical glitches with the audio. So if you can hear us, please just give us a sign. You can just pop a thumb either on Teams or on the YouTube channel. Then we know you are there. If you have a question, please feel free. We will also be able to see your questions from here. Feel free to type them in or just unmute your mic on Teams. Well, so we shall continue. True or false, during a collision between a truck and a pedestrian, the truck exerts a larger force on the pedestrian than the pedestrian exerts on the truck. So this is false. It doesn't agree with the Newton's third law, action and reaction. So the pedestrian and the truck will interact with the same equal forces, but opposite in direction. Okay, so I think for this section, that's all for FVV 101. If you have any questions with respect to this, please feel free. You can join us again tomorrow. We'll be live online to go on with the next sections and get you through them and see if you guys can attempt a number of questions and get assistance likewise. So I'm just going to take a short break and switch over to the PHYV 101 setup so that we can continue with a few questions therefore. So otherwise, don't go away. Just stand up and take a stretch, or you can even take a bottle of water or glass of water and drink. Then we'll resume within the coming 5 minutes. We'll have finished with the other setup. Okay. Okay, welcome back. All right, everything is set. So we will now look at questions from part 4 of the PHYV 101 questions. Yes, that's part 4. Good. So these are questions on work. So we will still apply some of what we have already learned from measurements, some of what we have learned from Newton's laws, and apply those concepts in answering some questions based on work and energy. So in our first question, a shopper in a supermarket pushes a cart with a force of 35.0 newtons, directed at an angle of 25.0 degrees below the horizontal. The force is just sufficient to balance various friction forces, so the cart moves at constant speed. Okay, you see? So already we are being told something about constant speed. That tells us something about the forces and the nature of the motion of this cart. So that's the cart, right? And what are we told about the cart? Okay, those will be the wheels there. And the force is 35 newtons at an angle of 25, so it's pushed. So if it's a push, then this is the direction of application. Right, that's the force, and it's 35 newtons, and the angle there would be 25 degrees. 25, did I get that right? Yes, 25 degrees. So the angle of application is 25 degrees to the horizontal, or 25 degrees below the horizontal as given there. So that means the force is just sufficient to balance various friction forces. So we have friction acting from the ground. Friction, subscript R. Let me use a small one. Friction acting opposite, and this force is just sufficient to counterbalance that, so that the cart moves at constant velocity v. Now find the work done by the shopper on the cart as she moves down a 50-meter long aisle. Right, so we're going through 50 meters, and in those 50 meters, what is the work done? So the work done there will be given by F cos theta, where theta is the angle between the net force or the applied force and the motion of the trolley. So theta should be the angle. In this case, the force responsible for motion has a component in the x. We call that Fx, right? So this is the force that has the effect of moving the trolley in the positive x direction through the 50 meters, right? So that force is just the horizontal component of the applied force. So say Fx cos theta, where theta now is the angle between this force and the direction of motion, right? multiplied by displacement, delta x. So the work done will increase as delta x increases. So fx is constant, then cos theta is also constant. So the work there will be a function of delta x. Now, this fx is what we need to find first. And so we say fx is equal to f, the applied force, cos 25 degrees. So it is the component of the force that is applied on the trolley at 25 degrees below the horizontal. So that component is f cos 25 degrees. So this angle, 25 degrees, is different from the theta that we use there. So you should take note. So since you use theta there, this you can call it alpha, the one, or you can call it beta, give it different names. But for the component, we are saying the component in the horizontal is f cos 25. Why cos 25? If the vector and the component that you are mentioning subtend an angle between them, then that component is a cos theta component. So we have a vector v, and we want a component in this direction of that vector. Then if theta is that angle, then this is a vector, let me just call it v, and this is the component of v component. So in this case, v component is therefore v component is equal to v cos theta. The vector and the component are subtending an angle theta in between them. So that component is definitely a cos theta component. If the angle is on the other side, right, or perpendicular to that, to the other component whose angle is mentioned there, then it means that component becomes a sin theta component. So in this case, we have perpendicular to the VC. So this is at 90 degrees, and we call this V sin theta. V sin theta will be perpendicular to V cos theta. Now you can see that between V, the vector, and this sin theta component, the angle there is not mentioned. If this angle is phi, it's not mentioned in the ratios. So the component that subtends the angle that is mentioned in the components is always the cos theta component. So it should be simple no matter what the orientation is, right? It should be simple for you to know where to give a component the right ratio to say it's a cos theta component or sin theta component. So if we want to mention this in terms of this angle, because the vector and the angle being mentioned is phi, then this component now becomes V cos phi, because we are mentioning the angle that's subtended between the vector and its component. So we call this V cos phi. So if you do V cos phi and V sin phi, they will give you the same. This will be the same value. If you can give values there, let's say theta is 30 and phi therefore becomes 60, sin 30 and cos 60 are all equal to 1/2. So this is true. So the cos theta component is the one that subtends the angle theta with the vector, right? So that angle which you mentioned is subtended with the vector by the cos theta component. Then, which means this one, therefore, VC becomes V sin phi. Sin phi becomes V sin phi there, which should equate to V cos theta. Cos theta and sin phi will be the same. So phi is 60, so sin 60, sin 60 is 0.8660 or root 3 over 2. Same applies to cos 30, is root 3 over 2. So this becomes the sin phi if the angle is on the other side. So you should find a way in which you can tell, or you can pick these components if they are not specifically given with the orientation that you are used to say the cos theta component is along the x-axis and the sine theta component is along the y-axis. It won't always be the case in the questions that you would come across. So you should know how you pick your cos theta, how you pick your sine theta. That should help you in tackling such questions. Okay, so besides that, we've said that fx is f cos 25. So f is 35. So we'll substitute 35 cos 25, then multiplied by cos theta. If our theta is 0 in this case, because fx and the displacement are in the same direction, the angle is 0. So that's cos 0, which is 1, multiplied by delta x, which is 50. So that should give us something there. Let's see what that 35 cos 25 multiplied by 50, 1.586 1.586 kilo, or times 10 to the 3 joules. So that's the work done. That's the work done, which is 1.6 times 10 to the 3 joules. Okay. So 1.59 there. This is so in this case you have to look at significant figures again. This is to 3 significant figures. You can give your answer to 3 significant figures. That would be very correct. So 1.59 times 10 to the 3 joules. Okay. Then part 2 says the chopper goes down the next aisle, pushing horizontally and maintaining the same speed as before. If the friction force doesn't change, would the chopper's applied force be greater, smaller, or the same? So if the chopper applies the force horizontally, then and the velocity doesn't change, then which means the value of f should be equivalent to what f cos theta was initially. So f cos 25, let's see what f cos 25 was, is 31.7. This is 31.7 newtons. So now, which means f is only being applied directly horizontally as 31.7 newtons to maintain the same velocity. So what can you conclude? What can we conclude? If the force is applied horizontally, then the force will be smaller. The force will be smaller. So it has no, the reason for this, does it say explain? It doesn't, right? But the reason for this is because when the force is applied as in the first case, right? That force has a component downward which adds to the reaction force. So the weight of the trolley plus the component of the force downwards would mean a greater reaction force. And that would also mean a greater frictional force. And with that greater with that greater frictional force, it means a greater force needs to be applied when dealing with when moving the trolley in this manner. A greater force, which is 35 newtons, should be applied when moving the trolley in that manner. Because remember, F equals to mu times R, right? The frictional force there is mu times the reaction force. So that reaction, because it's greater, the frictional force will be greater. But if the coefficient of friction is the same, when we just push it horizontally, then that component which was acting horizontally against friction is still basically the same. So that's the understanding there. The force will be smaller because we are applying directly that force to act against friction, right? That force to act against friction rather than having its component to act against the friction. So you can explain it in either of those two ways. Now, what about the work done on the cut by the chopper? So the work done should be the same. Remember, it's work done is the horizontal force times So this is work done on the cut. So that work done on the cut by the shopper is still the same work done because it's still the same horizontal force times the displacement. The same horizontal force times the displacement. So the horizontal force has not changed. So in the first case, some work was being done against friction. Extra work will be done against friction. That's why a greater force was applied there. But in this case, the work done against on the cut itself and not on anything else is still the same in both cases. So applying the force at 25 degrees in this case to the horizontal would mean the extra force that you're applying there is doing work on something else other than on the cut. The work that is done on the cut is due to the horizontal force, the horizontal component Fx, and as a result, the work done by the on the cut, right? The work done on the cut in both cases is the same. So you should take note what the question. What about the work done on the cut, right? The work done on the cut. But the work done by the shopper, in this case, the total work done by the shopper will be different. So it's only the work done on the cut. It is what is the same. Then question number 2. For question number 2, a block of mass 2.5 kgs is pushed a distance d equals to 2.2 meters along a frictionless horizontal table by a constant applied force of magnitude F equals to 16.0 newtons. So there is a block, a force applied at an angle theta, like in the previous instance. So it is pushed a distance 2.2 meters, which is a distance d shown there, along a frictionless horizontal table by a constant applied force F there, which is given as 16 newtons, directed at an angle of 25 degrees below the horizontal as shown in the figure. Determine the work done on the block by the applied force, by the normal force exerted by the normal force exerted by the table, and by the gravitational force, and by the net force on the block. So there are 3 things to consider there, or 4 things to consider, which are said to be doing work on the block, or which are acting on the block. So what is the work done on the block by the applied force? So this should be the same. This should be the same working. Work done on the block is F cos theta. So let's have that. Work done on the block equals to F cos theta. Okay, it's already called theta, right? And the component of this is the component acting at distance d. So we'll say cos phi. In this case, phi is the angle between the component in the x direction and the displacement. So times cos phi. Then multiplied by delta x. In this case, delta d. It's just given as d. Okay, let me call it delta d. So this is a 16 Newton force, cos 25 times cos 0, which is 1, and times 2.2. Times 2.2. So what do you get from there? What do you get from there? So that's 16 plus 25 multiplied by 2.2, 31.9. I hope you got the same, 31.9 newtons. So the work done on the block for the first part, the work done on the block by the applied force is 31.9 newtons. So this is for part 1. And part 2, for part 2, the normal the work done on the block by the normal force exerted by the table. The work done on the block by the normal force exerted on the table. What is that work done by the normal force on the table? So the normal force will be the reaction force, mass m, with its weight, which is due to m, it's called mg, and a reaction, some call it normal force. It's upward and opposite and equal in magnitude to mg, but this block moves in this direction, a distance d, to a new position which is there, right? So the question is, what is the work done on the block by the normal force exerted by the table? So this should be very simple because remember, work done is force times displacement. Force times displacement in the direction of the force. Now that the displacement is not in the direction of the normal, then that means because they are perpendicular, there is the work done there. We can say what work done on the block by the normal force. The first one, it was by the applied force, okay? So this, let's say it Wf, then by the normal force Wn equals to F or N cos 90 times 2.2, okay? Something like that. Cos 90 is 0, because this normal force is perpendicular to the displacement. So the angle between the displacement and the normal force is 90. So that makes the work 0. Same applies to the work done by gravity or by the weight. It will be 0. So for item 3, the gravitational force there will give the same 0 joules for the work, because it also acts at an angle 270, which gives cos 270 is also 0. Right, so the angle 90 is this one, and for gravity that angle is 270. So it's it will be W cos 270 times 2.2. So the formula will also give you that, but basically in principle, because the displacement and the force are perpendicular to each other, then there's no work done by those two forces. Now the next part says the net force on the block. What is the work done on the block by the net force on the block? So what are we told here? Horizontal table or along a frictionless horizontal table by a constant applied force of magnitude that. So if it's frictionless, then we don't have any opposing forces. So what will be the net force and what is the work done by that net force? What will be the net force and the work done by the net force? So in other words, the net work done on the block, right? So W net will be equal to So we have identified the work done by the applied force, which gives us 31.9 joules, right? Then the work done by the reaction force, or just accounting for all forces there, will be 0. The work done by the gravity is also 0. So the work done by the net force on the block is still 31.9 joules. So the net force does gives us that net work done, still 31.9 joules. Okay, so that's those are the solutions given there. Then question number 3. Question number 3. So for this one, we have a force F equal to 6I minus 2J, which is a magnitude of 6 in the X and a magnitude of -2 in the Y. Newtons acts on a particle that undergoes a displacement described by delta R, or vector R, equals to 3I plus J meters. Find the work done by the force on the particle and the angle between F and R. So the work done by this force and the angle between F and the displacement R. So we have the force described in terms of components. So there is force, it's given by 6I minus 2J, and we can try and represent that on a Cartesian. Okay, so this okay, just all right, that's better. So we have 6I. Can make it a sketch, still okay. So it's 6I minus 2J. So if that's 0, 2, 4, 6, 8, and minus 2, and 2, 4, 6. So 6I minus 2 is a vector that goes there. So this is the force vector, 6I minus 2J. Like that. So that's the force in newtons. And it acts on a particle that undergoes a displacement delta R. So the particle now moves just 3 steps in the I. So we can have this scale in red to be in newtons, right? Then we can choose another, the black one, to just show what happens there. So the part in meters, the black part is in meters, so we'll use the same scale. So the 3 is 3I plus J. The particle undergoes a displacement 3I and plus J. displacement of the particle is like that. So that's in meters. I plus j meters. Okay, so we have a different scale there. It's not basically the same Cartesian, but we're just showing a picture of what's happening in this system. So the work done by the force on the particle is what we need to find. And we know that our work done is F dot dr, right? It's F dot dr like this. It's a dot product between F and R, so we just do the dot product of F and dr because we're given this in terms of Cartesian coordinates. Okay, so F dot dr means that's where we get magnitude of F and magnitude of dr cos theta, cos the angle between them. Magnitude of F, magnitude of dr cos theta. In other words, is the component of the force along the direction R, right, which does the work. So it is that component multiplied by dr. So if we have a dot product like this, how do we do a dot product for two given vectors? A dot product for two given vectors. So F dot dr is equal to F is 6 minus 2 dot 3, 1. So we've taken 6. So we present a vector, a given vector, which is A, I plus B, J, as equal to A and B. So A represents the x coordinate, B will represent the y coordinate or the magnitude along the y. So this is what we've done. This is A, that's B, and that's A, that's B. Then we do our dot product multiplication like this. So what follows? What follows once we have a setup like this? What's the next step? What will be the next step? So a dot product is quite simply operated by multiplying the components in the x and the components in the y respectively, so that we just have 6 times 3, that's 18. So, and minus 2 times 1, that's minus 1. So the product there is such that our work done will be the magnitude of this resultant product. So in other words, you can put magnitude there. F dot dr is the magnitude of that. And what does that give us? Is it magnitude? No, it's not magnitude. It's supposed to be the other way. It's supposed to be like this. 6 times 3 plus 2 negative 2 times 1. So we just multiply the x components together and the y components together and add their products. So this will be 18 plus negative 2. And that gives us 16 joules. So the work done there is 16 joules. So it is x components multiplied with each other added to the product of y components added to y components multiplied with each other. So the x components are 6 and 3, which will multiply, and we add the y components, which is negative 2 and 1. That gives us 16 joules. So with this, then what that means is we can find the angle. Part B, we says find the angle between F and dr. So we can find that angle there by resorting back to this formula. This is where the magnitude will be applied, not here, not here. So this is just what we call the dot or scalar product. Scalar product. We'll multiply the respective x and y components and add their products. It's a scalar product. So with this, delta W, which is equal to 16 joules, is equal to magnitude of F, magnitude of dr, cos theta. And the magnitude of F is 6, root of 6 squared plus 2 squared. Plus the root of 3 minus 2 squared minus 2 squared plus 1 squared, which is the r vector, and cos theta, the angle between them. So that's root of 36 plus 4, 40, plus root of 4 plus 1, root of 5, which is basically the root of 200 times cos theta. So this is 16 over root 200, or root 40 times root 5. So this is the same as root 200. Root 40, is it plus? What did I do here? No. They're not multiplying. That's not acceptable. Hold on. Root 40. Yeah, they're multiplying. Why did I put times? So this is times, and this is root 200. I don't know where that plus came from. So they're multiplying the magnitude of F multiplied by the magnitude of dr times cos theta. Okay, so we then cancel here, and it means cos theta is 16 over root 200. So theta is arc cos 16 over root 200 over root 200. Arc cos 16 over root 200. Okay. I think something is not right there. root 40. Why am I getting a complex? Cos theta is that. That should be 36.9 degrees. Maybe this root 5 and 36 plus 4 is 40, root 40. Multiplied by 4 plus 1, 5 plus root 5 times root 5 plus 16 over 16, 6 and 3. Why did I put a 2 here? Sorry. So this is 6 and 3, so it's 6 squared plus 3 squared. That's 36 plus 9 root 45. Then no, I'm mixing up things. 3 and 1. Okay, now I see. Let's take it slow. I think I was too fast there. We have 6 and 2 there, so the magnitude of 6 and 2 is 6 squared plus 4 squared. That part was okay. Then here it's 3 and 1, so it's 3 squared plus 1 squared, so that's root 10. I think that should be root 450. All right, this should work. So not 200 but 400 here, and still we cancel that, but we have a 400 there. Let's see, arc cos 16 over the root of 400 is 20. Too much excitement. Arc cos 36.9. There we are. Yes, this is where we get 36.9. So that's 36.9 degrees. Arc cos 16 over 20. So what we have here is the magnitude of f. I think I looked at this. I don't know why I just looked at these products. Magnitude of f is 6 squared, root of 6 squared plus minus 2 squared. So the minus 2 is supposed to be there, but minus 2 squared and 2 squared are the same. They'll give us 40. And the magnitude of r, magnitude of r of the r here is 3 squared plus 1 squared, which is the root of 3 squared plus 1 squared, root of 10. And that's multiplied by cos theta, and if we divide by the part in the square root, there we have this giving us a root of 400, or just divide by root 40 times root 10, divide by root 40 and root 10 on the other side, and that gives us cos theta equals to 16 over 20. So theta will be arc cos 16 over 20, and we get that angle. Okay. So take note, for this problem, you should be able to do that dot product, and know that from the dot product, you have that relationship that gives you the angle between the vectors. So for your dot product, just multiply the x components added to the product of the y components. That will give you the magnitude of the product. In this case, 16 joules. So this is a dot product or a scalar product because we're multiplying two vectors and getting a scalar. We multiply two vectors and what we get is a scalar. That's why these products, it's the x product of the x components and product of the y components, then we add those magnitudes because it's just their products are just giving us a magnitude. So we add the magnitudes. Okay, so for our last question for the day, the last question for the day. Is this one. A 100-gram bullet is fired from a rifle having a barrel of 0.6 meters long. Choose the origin to be at the location where the bullet begins to move. Then the force in newtons exerted by the expanding gas on the bullet is. So we have a 100-gram bullet from a 0.6 meter long rifle. Then the question is, what is the force in newtons exerted by the expanding gas on the bullet? What is that force? So in this case, that force is given here as 15,000 plus 10,000 x minus 25,000 x. Would that be x squared? Where x is in meters. Where x is in meters. 10,000 x minus 25,000 x squared. I think this should be x squared. We'll see. So 15,000 plus 10,000 x, I'm sure that's a kind of a quadratic expression there, constant term in terms of x and term in terms of x squared, where x is in meters. So this is the equation describing the force in newtons exerted by the expanding gas on the bullet. Now the question is, determine the work done by the gas on the bullet as the bullet travels the length of the barrel. The work done by the gas on the bullet as the bullet travels the length of the barrel. So in this case, that length is generally the x, which is in that expression. So it's simply a case of substituting for x. Substitute for x. And determine that force first, then determine that force first. So this is it means the force is not a uniform force, it's a changing force. It's a non-uniform force acting on this, and it's dependent on the displacement or on the distance x in this system. So now we cannot apply the usual work force displacement formula, which is when a constant force is acting there. So what should we do then to find the work done? To find the work done. So we're told that the force in newtons is equal to 15,000 plus 10,000 x minus 25,000 x squared. So what is work in this case? We generally give work as F dx, like that. F times dx. So what do you think we do with such a question? So what that would mean is if we want w here, we have to integrate these two expressions such that the integral of delta w will give us w, and this will give us f, or integral of f dx with respect to x from 0 to x. Those are the limits. So in this case, our x is 0.6, so 0 to 0.6 of 15,000 plus 10,000 minus 25,000 x squared. And this gives us 15,000 x plus, so this is 10,000 x minus that. So this will be 10,000 over 2, 10,000 x squared over 2. When we integrate x, or when we integrate a constant, we introduce a constant is like with x to the naught. So we add the power, 1 to the power, and divide by the new power, 0 plus 1, right? So 0 plus 1 is 1, and x to the 0 plus 1 is x to the 1. So this is 15,000x. So we do the same. This is x to the 1. We add the power plus 1 and divide by the new power, 1 plus 1. So we get x to the 2 over 2. Then subtract 25,000 x to the 2 plus 1, which is 3 over 3, like that. So that's how we integrate. And now we substitute 0 and 0 to 0.6. So it is this expression times 0.6 minus 0, because everything multiplied by 0 is 0. So now 15,000 multiplied by 0.6 plus 10, we can reduce this to 5,000 multiplied by 0.6 squared minus 25,000 over 3 multiplied by 0.6 cubed. So what does this reduce to? 15,000 times 0.6 plus 5,000 times 0.6 squared minus 25,000 minus 25,000 over 3 multiplied by 0.6 cubed. This gives us 9,000, and since this is work, joules, 9,000 joules. So the work done by the gas as the bullet on the bullet as the bullet travels the length of the barrel will be 9,000 joules, or 9 kilojoules. Okay. Then if the barrel is 1 meter long, how much work is done? So if the barrel is 1 meter long, how much work is done? So we're substituting 1 into the same expression. So I'm just gonna replace the 0.6 with a 1 there. Every 0.6 with a 1. And what I'm getting is 11.7 kilojoules. 11.7 kilojoules. Okay. So the work with a distance of x equals to 1 meter will be 11.7 kilojoules. So you just substitute for the x in this expression, you substitute 1 for x. Substitute 1 for x. Same as we did when we substitute 0.6 for x. in the same expression. So you'd get 11.7 kilojoules. How does this value compare with the work calculated in part 1? So you can do a comparison there. 11.7 over 9. 11.7 minus 9. 11.7 minus 9 is 2.7. So it's more by 2.7. It's more by 2.7, which is basically 30%. So the work is greater by 30%. The work is greater by 30%. So there could be a rounding issue there with 11.7. What did we get initially? What was the exact thing we got there? 11.6666. Okay, so it's 11.6666 recurringly like that. So that would be 2.6666 like that, and that's there's the 29.6. So it's a rounding issue there. If you don't round your figure, you'll still come to the same answer. Looking at significant figures there, we have 3 significant figures. So with 11.7, yeah, 29.6, 29.7. I think it should be actually 29.6 is correct. It's correct. It's 29.6 to 3 significant figures. Okay, so that's it for today, guys. I hope you guys would learn something from this session, and this video will be live again tomorrow, and on the days to follow up till Friday online. So if there will be any change in the schedule, you'll be informed or you'll be notified once we are online. So I know you were writing your test today during the time we were scheduled to stream, but nonetheless what we needed to cover we have covered. So hope you will see this recording later. For those that were live, thank you for joining us. Let's meet again in the coming sessions on Yebo Physics. From me and everyone here at the studio, it's bye bye for now. Stay the best and all the best with your studies. Bye.